series day 6, I think. Page 3. Okay, lesson 2, guys. What else could we have changed x to? So if you make it negative x squared, that makes for a very interesting problem. Let's give it a try. So I want to make my x into negative x squared. Is this working? Let me make sure it works here. Yeah, there you go. Okay, so we're back on page 1's takeaway here. And we're going to change this x, and this x to negative x squared. Let's see what it looks like. This is now going to be 1 over 1 minus negative x squared. What's that going to look like? Good. In the sigma, we'll change this to negative x squared, as we said. In the inequality, we'll change this to negative x squared. Okay. Let's see what we have created here. I'd like to simplify this a little bit. For one thing, it's going to be a little hard to integrate. I am headed for arctan here in a minute, but I'm not quite ready to integrate. I don't like the way it's written. Let's rewrite some things. First of all, yeah, this can be rewritten a couple different ways. Why not write this as negative 1 times x squared all to the n? Same thing, right? In other words, negative 1 to the n times x to the 2n. I just think it's going to be easier to integrate that. Okay, so I'm going to kind of rewrite this part right here as negative 1 to the n times x to the 2n. The other thing I want to do is look at that inequality. So I'm looking right here now. Why don't you guys go ahead and solve that for x? Go ahead and solve that for x. You know, divide by negative 1, square root, all 3 parts. See if you can solve for x there. No, you don't actually. There's a redundant.
Awesome.
So when you divide by negative 1 on all 3 parts of an extended inequality, what do you have to remember to do? Okay, so this will become a 1. This becomes a greater than, right? This is now x squared. This is a greater than. This is a negative 1. Isn't x squared already greater than negative 1? Just by virtue of the fact that it's x squared, it's... Yes, so I'm just going to scratch that part. This is redundant. X squared is x is a real number. X squared is, yes, 0 or larger actually. So why not just call this greater than 0? Greater than or equal to 0. That's a little more meaningful. Or just have nothing there at all. Just here, solve it from here. You need to recall something for algebra 1 here. Okay. Now the way Mr. Lynch teaches this is when you square root both sides, you are supposed to include an absolute value here, because the square root of x squared is technically absolute value x. That's a great way to teach it. I love how he teaches it that way. This is just the same thing we started with. Negative 1 is less than x is less than 1. So somehow we came all the way back full circle. Your notes have it. My notes don't. But changing the x to a negative x squared here actually did nothing. That was kind of funky. We did several steps and we came right back to this fact. X is between negative 1 and 1. Okay, so now I'm ready to integrate. Okay? So let's take the antiderivative of 1 over 1 plus x squared. What's that? Inverse tan. Right. Ooh, we're supposed to integrate a series? How do you do that? Well, remember that a series is just really an infinitely long polynomial of terms. Okay? So it's actually extremely simple to do. If you were here yesterday, you saw me do it once already. But here's what's going on. This series goes like this. X squared minus, actually it starts out with just 1. It goes like this. 1 minus x squared over, no, 1 minus x squared. Sorry. This is 1 minus x squared plus x to the 4th minus x to the 5th, etc. That's all this is right here. It's not that complicated. That should be the 6th power. So it's just a bunch of even degree terms is all it is, like that. You could take the antiderivative of each one, or do it all in one big white buoy, where we just come over here and we just increase the power here by 1. That's what I'm going to do. So you can go through and integrate all of these if you want, and then try to rewrite a sigma. I'm just going to go right here. I'm just going to add 1 to my 2n. That's going to become 2n plus 1. This is like a coefficient, this little negative 1 at the end. This is just 2n plus 1. And then you're supposed to divide by the new power, you know, when you do the antiderivative. So what this does is this creates the terms x minus 1/3 x cubed plus 1/5 x to the 4th, 5th, minus 1/7 x to the 7th. So I did all the terms at once. I just kind of threw in an extra power there and put the new power on the bottom. Now we have a way to approximate arctan of something. Brand new formula. This is a third takeaway for today. This is called a Maclaurin series or a power series expansion for arctan. Okay? It's called a power series of arctan. So box it, it's a takeaway. Yes? Question? You sure?
I don't know if the Maclaurin series was just this one, or if it was all power series, but I'm assuming systems.
Just forget I said Maclaurin series. We'll come back to Maclaurin series later. I shouldn't have said that. A little out of context here. Okay, so, but what this means is that arctan looks like this. X minus, the first 5 terms would look like this. N equals 0 to 4, actually. So if you plug in 0, 1, 2, 3, 4, the denominators look like this. 1, 3, 5, 7, you see. It alternates signs, so it goes positive, negative, positive, negative. And this goes x to the 1st, x to the 3rd, x to the 5th, x to the 7th, you see. Now, obviously, this is not the same thing as arctan, but it's close. It's pretty close. If you want more accuracy, add a few more terms. You know. Okay, let's use our calculator. Let's get out our calculator now, and we'll find arctan at 0.5. And we'll also do 0.5 over 1 minus 0.5 cubed over 3, and 0.5 to the 5th over 5 minus 0.5 to the 7th over 7. Let's try typing both of these. Let's see just how accurate this thing is, the first 4 terms. Okay, so I typed in tan inverse 0.5, and it gave me this. 0.43, sorry, 0.463647609. And then I typed in the 0.5 minus 0.5 cubed over 3, etc. And I got, man, it's close, 0.4634672,619. Your absolute error here is less than 2 times 10 to the negative fourth. So we are close, we are like 1 in 5,000 error here. Super duper accurate. And that's only 4 terms, you see. So the error is less than 2 times 10 to the minus 4. Your absolute error. Pretty nice. Not bad at all. Okay, now let's go down and let's just kind of look at the curve of arctan versus the curve of this 4-term polynomial. Let's see how well they match graphically. Can I erase this? You got it? You got it there, Katrina? Katrina, you got it written down? Everybody got it written down? Okay. Here's the graph of arctan, obviously, right? If you just use the first term, it's just x. If you use the next term, it's x minus x cubed over 3. If you use the first, 3 terms, the first 3 partial sum, the third partial sum, I mean, it's got 1 extra term. Okay, so y1 just, of course, looks like this, kind of lame. Even that's a pretty good approximation, isn't it? Tan inverse is a rather straight graph. I mean, it's not a line, but in the middle it kind of looks linear, right? And I did a horrible job drawing that. I'd like to redraw. It's concave up on the left, so the line should be under. Concave down on the right, so the line is above. The linear approximation that we learned back in chapter 4 will now be upgraded big time. Now we're going to stick in a cubic polynomial that models the curve. Notice that it's actually a negative x cubed type cubic. See that? That means it's an upside down cubic. So this was y1. Here comes y2. Draw the right side of that a little bit better. Trying to get it to look like it hugs the curve a little more than the other did. This is y2, and it just does a better job of hugging the curve. It comes along, hugs the curve, stays close for a while, and then diverges apart. Right? y3 is a 5th order polynomial, or 5th degree, I should say, polynomial. And that's this green one. And it does an even better job grabbing the curve, hugging the curve, hanging on tight, but it does diverge away. And this is y3. Now I've exaggerated a little bit, okay? Probably that green thing I drew for you is more like y99. Okay? But I'm trying to get you to understand the idea that the polynomial comes in, hugs the curve, and then leaves. Right? But the polynomial is faithful to the curve between -1 and 1. That's the interval of convergence. Okay. Raise your hand if this is making sense. Good. I'll have it the other way. So if you wanted to hug longer and stay closer for longer in this nice little interval between -1 and 1, what would you need to do? Increase the number of what? Terms. Right. Yeah, it's like a relationship. The graph, the polynomial is either being faithful to the curve or not. The unfortunate thing about poor inverse tan is only between -1 and 1, if this is its lifespan, only between this small period of time will it ever have a polynomial that hugs it and loves it so closely. Okay? Because outside this interval, we have divergence, and it's horrible approximations. You would never, for example, use y3 ever to find arctan of 2, because that is way outside the bounds of convergence, and these polynomials do a horrible job. There's actually a way to shift everything over. Okay? There's a way to shift everything over and get the polynomials that hug the curve over here. But that's called Taylor series. We're not there yet. So what we're going to find later is we'll be able to pick any part of any curve and model it with polynomials. That's like the -1, +1, -1, +1 coefficients. Now, if you were integrating them term by term, you wouldn't do anything with those, right? They just stay there. Yeah, so the -1 at the end doesn't get integrated. It's like when you take the antiderivative of a negative object, it stays negative. So it just preserves the signs of the original. Okay, the other thing that didn't change was the interval of convergence. It was -1 to 1 before we integrated, and it was -1 to 1 after we integrated.
So
Okay.
does that ever change or no?
The endpoints sometimes change. So sometimes it goes from -1 is less than or equal to x is less than or equal to 1, and when you differentiate, you lose the endpoints.
Okay.
But you don't lose the radius of convergence.
Okay.
In other words, you don't lose how long the interval is, you only lose the endpoints maybe. That's another topic coming up,
Okay.
endpoint convergence. All right, good question. So this brings up one little tiny question. If we were to include all infinite number of terms, right, and it was like a beautiful curve that came in and just grabbed the red curve and just hugged it all the way through, would it hug the endpoints or not? Like, would -1 and 1 get touched by that infinite curve? That's a question for another day. That's called endpoint convergence. Does that perfect polynomial actually grab the endpoints or not? That's a series by series question we answer when the time comes. We're not going to answer that one about this. But your third takeaway is that this series approximates arctan between -1 and 1, and let's not talk about the endpoints today. What happens at -1? What happens at 1? Forget about it today, okay? So this is your third takeaway for this lesson. Where did this all start? Granddaddy Macho, right? The story all begins with this. This is what my teacher never taught me. I never knew where anything came from. But the story all starts with downward up there. That's our first step. All right. Let me go over this next page in the next few minutes here. This is a very wordy theorem, okay? It's super duper wordy, but it's very, very simple. Here's what it's saying. It's saying that if you want to take an old function, like 1 over x, and you want to take its derivative, you can also take the derivative of its power series representation at the same time. And you'll get a power series representation of the derivative of a function. For example, look at this crazy function here. Look at this goofball function that I gave you in example 1. What is f prime? Well, f prime is man, this thing's complicated. I think it goes positive, negative, positive, negative. I think it goes basically x to the first over 1 factorial, x to the 3 over 3 factorial, x to the 5 over 5 factorial, x to the 7th over 7 factorial, you see. That's complicated. But if you were taking its derivative, term by term, you would be consistently doing this, bringing down the power, right? Taking away a power. Bring down the power. Take 1 away from the power, right? And that's how you take derivative. You just bring down the power. Well, you could do that with all the terms at once. So what is going to happen if I take the derivative? What's going to happen to this guy? No, nothing will happen to him. He's responsible for creating the positive, negative, positive, negative, positive, negative pattern, you see. So when you take the derivative, that pattern is preserved. So he survives the derivative. What happens when you take the derivative of x to the 2n plus 1? First you bring down the what? You bring down the 2n plus 1. And then you take away a power. Now it's just 2n. Good. And the bottom is 2n plus 1 factorial, also known as 2n plus 1 times n factorial. So what theorem 1 is saying, listen, what theorem 1 is saying is feel free to take the derivative of a series. And theorem 2 is just saying feel free to take the integral of a series. It's that simple. These are just very wordy theorems. Okay? So there's your final answer, simplified. All right, I'm going to record the next 2 examples. But tonight you should rewatch page 2 if you need to. It's on video 1.